Okay, students, so good morning. Today we will cover the left portion of the mathematical statistics part. Okay. So today we will cover the topics like, first of all, we'll cover the central limit theorem. After that, we will cover the law of large number, and then after the estimation of population parameters using MLE and MME, maximum likelihood procedure, and the method of moments. Okay, method of moments. It's not MLE, it's methods of moments. Okay, and then after we have sampling distribution. Okay, so let's start with the first concept, that is central limit theorem. Okay, yeah, so start with first central limit theorem. So central limit theorem. Okay, so let me write this statement, that is, let x1 x2 dot 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 be a sequence of IID, independent and identically distributed random variables with mean expectation of xi is mu and variance of xi is sigma square, that is less than infinity. Okay, and let Sn is equal to x1 plus x2 plus dot 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 xn divided by n be a sample mean. Okay, it is a sample mean. Okay, then as n tends to infinity, means the value of n become large, say 100, 1000, 10,000, etc. Then random variables under root n is into Sn minus mu converge in distribution to the normal distribution of n0 sigma square, that is under root n into Sn minus mu will converge with distribution as normal 0 sigma square. Okay, or equally we can write it Sn distributed to normal mu sigma square upon n. Okay, now let's see the second part of this. Let x1 x2 xn be a random sample from an infinite or sufficiently large population with any distribution. Okay, it doesn't matter that which distribution you follow, like you can follow binomial, you can follow gamma, you can follow Poisson, you can follow uniform, any distribution with mean mu and variance sigma square less than infinity if n is sufficiently large, then, so what does it mean? If n is sufficiently large, then the sample mean x bar follows and approximate normal distribution, okay, with expectation of x bar is equal to mu and variance sigma square x bar is equal to sigma square, that is equal to sigma square upon n, okay. Then eventually what will happen? So equivalently x bar is distributed to normal mu sigma square n as n tends to infinity, okay, or z is equal to x bar minus mu upon sigma by under root n distributed to normal 0 1 as n tends to infinity, okay. So what did it mean? Like if x bar follow approximate normal distributions and its mu is mu and the variance is sigma square upon n, then x bar sampling distribution of sample mean will follow the normal mu sigma square n, or if we subtract the population mean mu and divide it by sigma under root n, then it follow normal 0 1, okay. Now what is a sufficiently large, okay, like here I have written that n is sufficiently large. Then what is sufficiently large? Okay, then let me write it. What is sufficiently, when should you use the central limit theorem? Okay, let me change my color. Okay, so first is if population distribution is symmetrical, unimodal or continuous, then a sample size as small as n is equal to 4 or n is equal to 5 is enough, okay. Then the second for is if the distribution is skewed, okay, then n should be greater than equal to 30 can be adequate, okay. And if the distribution is extremely skewed, then n is should be greater than equal to 50, or even n is greater than equal to 100 may be needed. So these are the values of n. Let me highlight that, okay, that should be you use when you are try to use the central limit theorem. So this is the concept of the central limit theorem that I have written here, okay. Now we will move forward to next topic, that is law of large number, okay. So what is law in law of large number, okay, we will see some of the important terms, okay. Okay, so let me start. Yeah, when the extremely strong assumption, okay, when the extremely strong assumptions of the classical normal linear model do not hold, okay, we often use asymptotic theory to test hypothesis and form confidence interval. Okay, so when the extreme strong assumption of the classical normal linear regression model do not hold, we use the asymptotic theory of test of hypothesis and the form of confidence interval. Okay, now asymptotic theory depends on two types of fundamental results. Okay, and what is that? That is law of large number and central limit theorem. Okay, law of large number and the central limit theorem. Okay, so central limit theorem we have discussed earlier, and now in this we will see the law of large number. Okay, so let me write law of large number. So a law of large number, or we can set LLN, it's not LLM, large language model, it is LLN. Okay, may apply to anything that can be written as an average of n random variables. Okay, now let me give a small definition of the LLM. That is, let xi is equal to I is equal to 1 dot 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 n be independent random variables, each with bound finite variance, sigma I square, and with a common mean mu. Okay, so sample mean of xi's are x bar is equal to 1 upon n sigma xi n I is equal to 1. Okay, so a fairly simple LLN says that as n tends to infinity, xn tends to mu. Okay, now we will see. So this is a law of large number. Okay, so what does it mean? It's mean that if xi is 1 to 1n be an independent random variables, each with the bound finite variance as sigma square and a common mean. See, common mean we have written mu. So a sample mean is what? Sample mean is just x bar is equal to 1 upon n sigma xi. So a fairly simple LLN, what's if n tends to infinity, like if n become 1000, 10,000s, then x bar tends to the population mean. Okay, now we will see a important formula, that is weak law of large number. It is very important. Okay, so what is weak law of large number? So I am just writing the statement and I am not going to prove it. Okay, because the proof is not very important for your JAM exam point of view. Okay, so and you will find the proof in any statistics book. Okay, let x1 x2 xn be a sequence of random variable and mu1 mu2 dot mu n be the respective expectations, and let bn is what? Bn is nothing but it is the variance of x1 x2 dot x, not variance of, it is in addition dot plus xn, that is less than infinite. Okay, then probability of x1 x2 dot plus xn divided by n minus mu1 plus mu2 dot plus mu n divided by n less than epsilon is greater than 1 upon n phi. Okay, for all n greater than n naught, where epsilon and it is not t, it is planet, and phi theta are arbitrary small positive number, provided limit n tends to infinity beta n upon n square tends to 0. So this is the condition of weak law of large number. What it say? If x1 x2 is the sequence of random variables and mu1 mu2 with respective expectations and variance is just in edit form, then if you write in the different form, we will write that x bar minus mu less than epsilon is greater than 1 upon phi. See, this is what we have seen in the law of large number. Okay, it is 1 minus here. So yeah, for all the n that is greater than n naught and where epsilon and phi are the arbitrary small positive number with limit bn divided by n square tends to 0. Okay, let me see. Yeah, and then we have 1 minute, and then we have a weak law of large number for the independent identically distributed random variable. Okay, this is for the sequence of random variable. Okay, see here, it is not IID because there is nowhere written that's independent and identical. Okay, now I will write the, so I am write the abbreviation like weak law of large number for IID, that is independent identically distributed random variables. Okay, what does it mean? Now let me use yellow. If x1 x2 dot xn are independent and identically distributed, okay, and expectation of xi is equal to mu and variance of xi is equal to sigma square for all I is equal to 1 to at n, then bn is what? Variance of x1 plus x2 plus dot plus xn. Since all the variants are same, that way can we write it variance of xi for all n, and that is equal to n sigma square, because since each of the variance is sigma square, then sigma square plus sigma square plus sigma square up to the n term, that is n sigma square. Okay, the covariance term will be vanish. Let me write covariance term vanish since the variable are independent. Okay, so limit of n tends to infinity beta n upon n square is equal to limit not equal to limit n tends to infinity sigma square upon n is equal to 0. Okay, then the weak law of large number holds, let me write, then the weak law of large number hold for sequence xn of IID random variables. We get probability of, see, I am writing the above form, that is, I am writing this form. Okay, that is probability of x1 plus x2 plus dot 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 plus xn minus n minus mu less than epsilon is greater than 1 upon n for all n is greater than n naught. Okay, that is what it's mean. That is probability of xn minus mu is less than epsilon is equal to 1 as n tends to infinity, and probability of x1 minus mu is not like this, it is epsilon is equal to 0 as n tends to infinity. What does this mean? Okay, this is statement and this is statement. What does it mean? Okay, so the results implies that that xn bar, that is sample mean, convergence in probability to mu. Okay, that is, let me write in formula, xn bar converge with probability to mu. That is what's weak law of large number means. Okay, so this is weak law of large number for the independent identically distributed random variables, like the sample mean will tends to the population mean. Okay, now I will see one important formula, that is Kinchin theorem of weak law of large number. Okay, that is simply formula, I just write it here, that is Kinchin theorem. See, this theorem is not important for the JAM point of view, I just write it here for your future knowledge. Okay, what does that mean? If x size I is equal to 1 to dot 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 n are IID, it is same that I have written here. Okay, IIDs random variable with expectations of xi is equal to mu less than infinity, then x bar and converge with probability to mu. See the same thing which I have written above. Okay, there is one more formula that I have, I think I should write it. Okay, it may possible that the question directly come in your examination, but that probability is too low. Okay, you should know. Okay, so see, let x1 x2 dot 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 xn be IID variables with mean mu and variance sigma square. Okay, as n tends to infinity, you have to show x2 square dot 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 xn square divided by n will converge with probability to c for some constant c, where c is between infinity, and you have to find c. What this question mean? If x1 x2 and xn are the IID random variables with mean mu and variance sigma square and n tends to infinity, and you have given this formula, and you have to show that this x1 square plus x2 square dot 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 xn square will converge to c with probability with some constant, and you have to find the value of c. Okay, so let's to solve it. See, we are given that what xi is equal to mu. Okay, variance of xi is equal to sigma square. Now what is expectation of xi square? You should calculate it with the formula of variance of xi plus sigma xi square whole. Okay, that is what is variance? Sigma square plus mu square. Okay, now by the theorem that I have written here, Khinchin theorem, by Khinchin theorem, weak law of large number holds for the sequence of xi square of IID. What does it mean? It's mean xi square plus x2 square plus dot 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 xn square divided by n will file the probability with xi squares as n tends to infinity. Why it is possible? See, when x1, see in Khinchin's theorem, when x1 plus x2 dot 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 xn divided by n tends to mu with probability, and what is mu? That is expectation of x. Then it is possible that x1 square plus x2 square plus dot 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 xn will fall the exi square. Okay, then just put it here. Since square upon n will converge to p, and what is the value of exi square? It is given sigma square upon, that is sigma square plus mu square, and this is your answer. Then what is the value of c? The value of c is nothing but sigma square plus mu square. Okay, so this is what we have to prove, because Khinchin's theorem, what it say? We say that if xi's are the IID random variables with mean expectation of xi is equal to mu less than infinity, then your sample mean tends to mu. Okay, then by this theorem we can prove that if x1 square plus x2 square dot 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 xn square divided by n will tends to exi square. Okay, then by Khinchin's theorem, exi square is what? Sigma square upon mu, sigma square plus mu square, and it is what we have to prove. Okay, so the law of large number is also completed. Now we will look the now we will look about this sampling distribution. Okay, so let me start the sampling distribution. After sampling distribution we will look the method of estimation. Okay, so let me write here sampling distribution. Sampling distribution. Okay, so what is sampling distribution? Okay, so before sampling distribution we should know about some of the concepts. Okay, what is concept? That is, first of all, is population. First of all is population. See, I have already taught about the population samples in the previous part of the mathematical statistics. Okay, I just give a short form here. What is population? So population is a, I just recall it here, a population is the entire set of individuals or observation of interest. Okay, for example, all patients in the hospitals, all patients in hospital, all voters in a country, etc, etc. Okay, and what are some populations parameters that is important in today's sampling distribution? So population parameters will be say mean. For mean we use mu. For variance, population variance, we will use sigma square, and for proportion we use p. Okay, now then after population we have the sample. What is sample? Sample is nothing but a subset of the population selected for analysis, and it should be the representation of the population. Okay, for example, if all patients in hospital, then what is the sample? 500 patients selected from hospital. Okay. Okay, now what is the sample parameters? Sample parameters will be sample mean, that is nothing but x bar, sample variance, that is nothing with small s square. See, is it small s square? Okay. Sample proportion, that is small p. Okay. Now we will come to the sampling distribution. Okay. Just 1 minute. Not this. Okay. Let's come to the sampling distribution. Sampling distribution. So what is sampling distribution? So a sampling distribution is the probability distribution of a statistics. Okay, like mean or proportion computed from all possible samples of a fixed size drawn from a population. Okay, so what is sampling distribution? So a sampling distribution is a probability distribution of a statistics computed from the all possible samples collected in a fix. Okay, so I will write some of the key properties of the sampling distribution. So let me write the key properties, that is key properties of sampling distribution. What is, first of all, mean of sampling distribution, that is expectation of x bar is equal to mu. Second is variance, that is variance of x bar is equal to sigma square upon n. And third is standard error, that is standard error of x bar is equal to sigma by under root n. Okay. Okay. Now before that, yeah, so this is the some key definitions and the terms for the sampling definitions. Okay, so in sampling distribution you have to collect the samples. What I have written here, the in probability distribution of the statistics computed from all possible samples of the fixed size. Now how will you collect the samples? Okay, so there is I have already taught, that is simple random sampling, but I should recall here, that is you can collect sample by simple random sampling. Okay, so let me write it. What is simple random sampling? So a simple random sampling is what? Simple random sample is an equal probability sampling, mean each sample is selected with an equal probability. Okay, and there is two types of SRS, that is SRSWR and SRSWOR. What does it mean? It's mean simple random sampling with replacement and simple random sampling without replacement. Okay, I will define these both terms here. Okay, so don't no. What is SRSWR? So suppose a small, sorry, not small, a sample. Suppose a sample of n units is drawn from the population of size n, one by one, with replacement. Okay, so the number of possible sample would be n to the power n. Why? See, because we have the population size n, and we let me use different color. We have the population size n and we have to sample n units with replacement. So for example, if you have 5 balls and you have to draw one ball, so you have drawn one, but after the in the next draw you should keep the first ball again into the box, and then again you have to draw it. So all the possible number of possible samples will be n to the power n. And what would be the probability? And the probability of selection would be 1 upon n to the power n. Okay, now second, what is SRSWR? So same here, suppose you have to draw the n unit from the population size, but here it is what I am not writing the whole statement. I without replacement, all are above is same, without replacement. Now what is the total number of sample size? So number of possible sample will be n to the power n factorial. Why here it is? Because here you have replaced. For example, from 5 ball you have drawn one, but after the next ball you have draw, you will draw from the remaining, that is from the 4 balls. So that's why you will say here in SRSWR we use the factorial. So what is the probability? And probability of is equal to 1 upon n to the power n. It is probability here. Okay, yeah, so that is the that is the probability of not probability, that is the simple random sampling with replacement and simple random sampling without replacement. And another term that is very important, that is standard error. So what is the standard error? See, let me write the definition first. Sampling distribution of a statistics T is a probability distribution, and it has mean, variance and higher order moments. Okay, the standard deviation of the, it is a standard deviation of the sampling distribution of the statistics T is called the standard error of the statistics. Okay, what the standard deviation of the sampling distribution of the statistics is called the standard error. And how will you define the standard error? So standard error can be defined as under root variance of T, that is nothing but expectation of T minus expectation of T squared half. So this is your standard error. Okay, now we will come some of the distributions. Okay, some basic distributions. Let me write what we will now come. Yeah. Some basic distribution useful in finding sampling distribution of statistics. Okay, here we will see about chi-square distribution, t distribution, f distribution. Okay, yeah, so let's start. So first of all, I will start with the chi-square distribution. Chi-square so what is chi-square distribution? Okay, I'm sorry. So chi-square distribution is if, not if, let x follow a normal mu sigma square. Okay, then z follow what? X minus mu upon sigma will follow normal 0 1. Okay, then z square, that is x minus mu upon sigma square, will follow a chi-square distribution with 1 degree of freedom. Okay, okay, that is in general. I will write a general condition. If xi is equal to I is equal to 1 dot 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 n are n independent normal variate with mean mu and variance mu I and variance sigma square, then chi square, that is sigma n I is equal to 1 xi minus mu I upon sigma square follow is a chi square variate with n degree of freedom. Okay, now I will show you what is the distribution of the chi-square. Okay, so PDF of chi-square. So the PDF of the chi-square is 1 upon 2 to the power n by 2. See, you don't want to see the proof of the PDF of the chi-square because that is not very important. You just remember the PDF. Okay, e to the power minus x square by 2, not x square into 1 minute, that is not x square here, it is chi square. Let me write it more clear. 2 okay, now one more important, and we will now, so this is your PDF of the chi square. Okay, now see some important property first. If x follow a chi square with n degree of freedom, 1 upon 2 x follow gamma 1 upon 2n. Okay, so this is what, if x follow the chi square n degree of freedom, then you will see the x, if you have x is a random variable and you will divide by 2, then it will follow the gamma 1 by n by 2. Okay, now now we will see the mean and expectation of the chi-square distributions. Okay, so for a second, mean of suppose x follow the chi-square distribution with n, then mean expectation of m mean is n and variance of x is 2n. Okay, and there is some, yeah, okay, and then we have the mode, and the mode of chi-square distribution, chi-square distribution will n by 2. Okay, now there is an additive property. Additive property of chi-square variate, and what is that? The sum of the independent chi-square is also a chi-square variate. Okay, what does that mean? Sum of independent chi-square variate is also a chi-square variate. Okay, that is, if x1 follow chi-square 1 degree of freedom, x2 follow chi-square 1 degree of freedom, then x1 plus x2 will follow chi-square 2 degree of freedom. That is what it means, that chi-square variates are independent, chi-square variates are additive in properties. Okay, so these are some chi-square conditions. Then I just see what is anything important. Not okay, so this is for the chi-square, and there is some of the sample statistics parts as well, so we will look here. Okay, now what is the, I'm sorry for this, yeah, that is important theorem. What it say? Let x size, not x size, x1 x2 dot 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 xn be a random sample from a population, not population, from a normal population with mean mu and variance sigma square. Then first condition, x bar follow normal, mu sigma upon n, then sigma xi minus x bar upon sigma square will follow chi-square with n minus 1 degree of freedom. Why? Because see, it is not because it is not the x, it is the x bar here, we are using the x bar here, that why it will follow with n minus 1 degree of freedom. Okay, okay, and this, if x bar is equal to 1 upon n sigma xi, then n square upon sigma square, that is equal to 1 minus x bar upon sigma square. Okay, how it will become, we will see again, and it will follow another chi-square with n minus 1 degree of freedom. Okay, okay, now we will see the formula that sorry. Okay, now see solution, not solution but see. So what is the PDF of the sample variance? So PDF of sample variance is what? It is important. PDF of sample variance is what? Small s square is equal to 1 upon n sigma xi minus x bar square. Okay, now you just don't do anything. See, s square is equal to 1 upon n sigma xi minus x bar square. Okay, now put the n here, that is n s square is equal to sigma xi minus x bar square. Now divide both sides by sigma square. What is this? Sigma square, that is sigma xi minus x bar by sigma whole square, that is nothing but chi square with n minus 1 degree of freedom, because it is for the sample variance, it will for not sample, it is for the sample mean. Okay, sorry why it's happening. Yeah, now okay, so now we know that n s square upon sigma square will follow chi square with n minus 1 degree of freedom. Then what will be the sample mean? So expectation of n s square is sigma square, that is n minus 1. Okay, and what will the variance? So variance of that is 2n minus 1. Okay, yeah, that is. So you always write, always remember that n is sample variance divided by sigma square is equal to chi square with n minus 1 degree of freedom. Okay, so this is, I think, all for the chi square. Now we will move for the t distribution. Okay, let me just open my t distribution. T distribution. Okay, so what is t distribution? So first of all, we'll write upon student t distribution. So what is student t distribution? So let's say xi's are random sample of size n from a normal population. Sorry guys for this. Okay. Normal population with mean mu and sigma square. Okay, then student t does student t statistics is defined as x bar minus mu upon s by under root n. Okay, where x bar is 1 upon n sigma xi square and s square is upon 1 upon n minus 1 sigma xi minus x bar square. Okay, and what is the PDF of this distribution? So PDF of t distribution is ft is equal to 1 upon v. I will define what is b. b 1 upon 2 v by 2 into 1 upon 1 plus t square upon v, so 1 by 2. This is your distribution. So what is v? So v here is nothing but n minus 1 degree of freedom, and this is beta function, beta 1 by 2 into v by 2. Okay. So the derivation of this statistics is not quite important. So basically the difference between the t and z test is that t distribution or t test we are using when we don't know about the population variance. See here also the the variance is calculated from the sample itself, but in z distribution the population variance are known to us, but in t distribution or the t test the population variance is not known to us. We are calculating that from the samples that is available. Okay, now we will see a Fisher T. Fisher T definition. What does it mean? Suppose x is a random variable that follow normal 0 1. Okay, and there is a chi-square distribution. Then the Fisher T can be defined as x upon under root chi-square upon n degree of freedom. So this is the Fisher T distribution. What is Fisher T distribution? A ratio of the standard normal variate upon the under root of chi-square distribution divided by the n degree of freedoms. That is what the Fisher distribution. Okay, yeah. Then we see the moments. So what are the moments? So first of all, since ft, that is the T distribution, is symmetrical around line t is equal to 0, so all odd moments of T distribution is 0, means the mean of the T distribution is 0, but variance is not an odd moment. So variance is upon what? So variance is n divided by n minus 2. Okay, always remember all the odd moments, mu1, mu3, these all are 0 in the T distributions because it is symmetrical. Okay. Okay, now we will see some of the applications of the T distribution. Application of T distribution. So first is t-test that were used in the regression analysis for single mean. So what is the t-test for the sample mean? Okay, so the samples are drawn from the population. That is first samples are drawn from population with mean mu naught. So the test statistic x bar minus mu naught upon s divided by under root n. Okay, where x bar is equal to 1 upon n sigma xi and s is equal to under root of 1 upon n minus 1 sigma xi minus x bar square. And what will it follow? It will follow t n minus 1 distribution. Let me write it here. And it will follow t n minus 1 distribution. Okay, and you have to see the critical value of n minus 1. Okay, now the another is that t-test for the difference of mean, and the second t-test for difference of mean. Okay, so suppose we want to test if two independent sample, we have two independent sample, we have two independent sample, that is x1 and dot is 1 1 and we have y1. So null hypothesis is what? That the sample has been drawn from the normal populations with mean mu x and mu. So I just write the test, that is x bar minus y bar minus mu x minus mu y divided by s under root 1 upon n1 plus 1 upon n2. Okay, so this is your T statistics for the difference of the two mean. And what is s square here? It is nothing upon 1 upon n1 plus 1 upon n2 minus 2 sigma xi minus x bar square plus sigma yj minus y bar square. Okay, and what will be the degree of freedom? It will follow n1 plus n2 minus 2 degree of freedom. So you have to see this critical value, you have to see this critical value. Okay, So okay, this is for the t distribution. Now we will see the f distribution. Yeah, 1 minute. Okay, so let's see the 1 minute. I should add 2 more pages. Now we will come to f distribution. F distribution is very important for your examinations because the concept of the F distributions are used in the regression analysis. So what is F distribution? So let if x and y are two independent chi-square variate with v1 and v2 degree of follow sorry, degree of follow and degree of freedom, I'm sorry, then f statistics will be defined as x divided by v1 divided by y divided by v2. This is your f statistics. Okay, means in form chi-square divided chi-square v1 divided by v1 degree of freedom divided by chi-square v2 divided by v2 degree of freedom. This is what your f statistics. And what is the PDF? So when you talk about the PDF, you will have v1 upon v2 upon 2 divided by beta function v1 upon 2 2 upon 2 into f v1 divided by 2 minus 1 into 1 upon v1 by v2 f into v1 plus v2 divided by 2. Okay, so this is the PDF. And one of the important point is here is that the sampling distribution of f statistics does not involve any population parameters. You will see that the f statistic does not involve any population parameters. It only depends on degree of freedom. Okay, so f statistics does not involve any population parameter. It depends on degree of freedom. Okay, so let move to the mean of the so mean of f distribution. What will the mean of the f distribution? The mean of the f distribution is v2 upon v2 minus 2. See, v2 is the degree of freedom of the y. Okay, and what about the variance? So variance will be 2v2 square into v2 plus v1 minus 2 divided by v1 into v2 minus 2 square into v2 minus 4. It's greater than 4. So this is the mean, and so where v1 and v2 are degree of freedom of x and y, means chi-square v1 and chi-square v2. Okay, and what is the mode? So mode is v2 upon v2 plus 2 into v1 minus 2 upon v1. Let me write it more clearly. v1 degree of freedom of x1, so x square v1 x square v2. It is what x, it is what y. Okay, okay. Now there is, sorry for this, now there is one of the important property of the f distribution that I have to write it. If f n1 n2, it is denoted by like this, f n1 n2, where n1 n2 represent the, let me write it here, represent and f variate with n1 and n2 degree of freedom, then f n2 n1 is distributed as 1 upon f n1 n2. What did it mean? It's mean probability of f1 distribution f1 f2 greater than c is equal to probability of f n2 n1 is less than 1 upon c. Okay, I'm not going to the proof of this, but I just written the formula here. Okay. I am saying that if any so I'm continuing from the last portion. Okay, sorry, I have to off the video due to some of the technical glitch, so I'm starting from there. Okay, now I will show some of the relationships between the t distribution and f distribution, and then after relationship between the f and the chi. Okay, so it is important. Relationship between t and f distribution. Okay, what is the relationship between the t and f distribution? See where it is. If statistics t follow student t distribution with n degree of freedom, then t square follow f distribution with 1n degree of freedom. What is it? Say if t follow tn, then t square will follow f1n. How? Let me write it. Suppose x follow normal 0 1. Okay, and y follow chi square with n degree of freedom. Okay, so what is t distribution? So t distribution x upon y upon n. Now take the square both side, that is x square upon y upon n. So when you see x minus 0 upon 1 square will follow what? Chi square with 1 degree of freedom. So it will be equal to chi square with 1 degree of freedom 1 upon y, and y is what? Y is here chi square n degree of freedom divided by n. So what is that? It is f distribution with 1 upon n. So this is the statement what is said. Let me explain it one more. Suppose x follow normal 0 1 and y follow chi square distribution with n degree of freedom. Okay, so what is the t distribution? T distribution is x is the ratio of the standard normal variate divided by the under root of chi square distribution divided by with degree of freedom. Now when we take the square on both sides, what will we have? We have x square. So when we take the square of this x that follow the normal 0 1, we get what we get? We get chi square with 1 degree of freedom. So and the under root will be cancel out, that is chi square with 1 upon factorial 1 divided by 1 divided by y upon n, that is what? F distribution with 1n. Okay, so this is the relationship between the t and f distributions, and now I am going to start the last portion, that is the method of maximum likelihood estimation. Method of maximum likelihood estimation. Okay, so this estimation was first introduced by the R.A. Fishers. Okay, So let me define. First of all, we define the likelihood function. So what is likelihood function? Let me write. So let x1 x2 dot 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 xn be a random sample of size n from a population with density function fx theta, where theta is a parameter. Okay, likelihood function of x1 x2 sample values are denoted by L theta is their joint density function, that is L is a what, fx1 theta fx2 theta dot 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 dot, that is fxn theta, that is pi n I is equal to 1 fxi theta, where okay, where L gives the relative likelihood that the random variable assume a particular set of values x1 x2 dot 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 xn. Okay, now the principle of maximum likelihood consists of finding an estimator for a known parameter theta, that is equal to theta 1 theta 2 dot 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 theta k, which maximize the likelihood function L theta. So what is the principle of maximum likelihood estimation? The principle of maximum likelihood estimation means we have to find an estimator of a known parameter theta which maximize the likelihood function. Like we have to find that parameters that maximize this sample, that's a sample, yeah, likelihood function, not sample, likelihood functions. So we wish to find theta, that is theta 1 theta 2 theta n, that is L theta is greater than L theta, means that the likelihood function will be maximum from the remaining likelihood functions where theta is a parameter space. Okay, now okay if there exists a function theta cap, see, always we use the theta cap to define the MLE. Okay, that is the estimated value of the estimator. Theta cap x1 dot dot xn of the sample values which maximize L for variation in theta, then theta cap is to be taken as an estimator of theta. Okay, and theta cap is what we call it. We'll call it MLE, maximum likelihood estimator. Okay, see, I know the definition is quite very hectic, so I will go with solving the examples so that you can get a clear idea. Okay, now before that, there is some of the important properties. Okay, that is very important for the MLE. So what are the important properties? So first is MLEs are always consistent estimator. Always remember, MLEs are always consistent estimator, but need not be unbiased. Okay, always remember, your MLE may be biased, but it always be a consistent estimator. Okay, now okay, now the next is, if MLE exists, it is most efficient in the class of such estimator. What does it mean? If MLE exists, okay, then it will be the most efficient in the class of such estimator. And the third is, if a sufficient estimator exists, it is a function of, I am already talked about the sufficient estimator, function of the maximum likelihood estimator. Okay, so these are some of the properties of the maximum likelihood estimator. Okay, now let me take some of 1 or 2 examples so that you can get a very clear idea. So what is question 1? Let me write the question with red. Okay, so what it say? Suppose if x1 x2 dot xn follow a normal mu sigma square. Okay, we have to find the MLE of mu. Okay, let me write mu when sigma square is known, means we know about the sigma square. Then second, sigma square when mu is known. And the third property is, we have to find for both sigma and mu square. Okay, so in the first case we have to find the mu, but we know sigma square. In the second case we have to find the sigma square, but we know mu. But in third case we don't know anything, we have to find mu and sigma simultaneously. Okay, so let's start for first case. Okay, so x follow normal mu sigma square. Okay, so L is what? Pi n I is equal to 1 fxi mu, that is 1 upon 2 pi under root sigma square, it is power 1 upon 2 x minus mu square upon 2 sigma square. Okay, by power n. And how will you write it? You will write it like this: 1 upon sigma under root 2 pi n e exponential sigma n I is 1 xi minus mu square upon 2 sigma square. Okay, take the log. Why we have taken log? Log is an increasing functions, that's why we can take it. Minus n upon 2 log 2 pi minus n upon 2 log sigma square minus 1 upon 2 sigma square, and I is equal to 1 psi minus mu square. Okay, now since mu, we know the mu, we have to differentiate with respect to we have no sigma square, so we will differentiate d log L by d mu and equates to 0. So when we differentiate this term, it will become 0. When we differentiate this term, it will become 0. And when we differentiate this term, we will get sigma 2 xi minus mu into minus 1 is equal to 0. Okay, now it is simple differentiation. Okay, so here what we get, 0, so mu is what, x bar, so mu x bar is the MLE of mu. Okay, okay, so now case 2, we know, so mu is known, so we differentiate with d sigma square log L, and what will you get here, we'll get minus n by 2 into 1 upon sigma square plus 1 upon sigma 4 sigma n I is equal to 1 xi minus mu square is equal to 0. Okay, that will equal to n minus 1 upon sigma square sigma n I is 1 xi minus mu square is equal to 0. Okay, so sigma square cap, that is equal to 1 upon n sigma xi minus mu square. This is what we gave for sigma square. Now in third I will give just a hint, you will try to solve it. Just use this d mu log L is equal to 0 and d log L d sigma square is equal to 0. Okay, you will get an estimate. Okay, and it will be same for this case and for mu it will be. Okay, okay, so now we will try for the Poisson distribution. Okay, so let's try for the Poisson. Let x1 x2 dot 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 x follow Poisson distribution with lambda, and you have to find the MLE. Okay, find the MLE for lambda. Okay, so what is the probability of x is equal to, x is what, e to the power minus lambda into lambda x upon x factorial is equal to 0 1 2. Okay, so what is the likelihood function, just use this. See, if you are practice 2 or 3 4 questions, then it become easy for you. Okay, and lambda into lambda sigma xi upon x1 not x1 x2 dot 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 xn factorial, it is factorial. Okay, now take the log both side, log L, that is equal to minus n lambda plus n x bar log lambda minus sigma n I is 1 log xi lambda. Okay, not xi factorial. Okay, now d log L upon d mu is equal to 0, so what we'll get, n plus n x bar upon lambda is equal to 0. From here what we for lambda, so this is the MLE. So always remember, for which parameter you have to find the MLE, you have to differentiate with that. Okay, okay, so now we will see the another concept, that is the method of moments. Okay, let me go, and this is the last topic for the mathematical statistics portion. After that its portion is completed. Method of moments. Okay, what did it mean? See, let fx theta 1 dot 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 theta n be density function of the parent population with k parameters mu1 mu2 dot 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 mu k. Okay, and if mu r denotes the rth moment about origin. Okay, then mu r is what, describe it, xr fx theta dx. Okay, okay, so now in general mu1 dash mu2 dash dot 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 will be function of parameter theta 1 theta 2 dot 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 theta k. Okay, now the method of moment consists of solving the kth equation. Okay, in this equation 1, kth equation in 1 for theta 1 theta 2 dot 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 theta k in terms of mu1 dash mu2 dash dot 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 mu k, and then replacing these moments mu r by sample moments. Okay, I will show by example how will you make it. Okay, it is just a formal definition, you should know. Okay, theta I m1 m2 dot dot dot. Okay, yeah, so I will solve one question. Okay, so start. See, these are the definitions, and the definition would not come in examination, so you know how to solve it. Okay, now example. Estimate alpha and beta. Okay, alpha and beta by method of moments. And what is the distribution? So distribution is this. I will take a different distribution, not a normal or binomial. Okay, how will you solve it? Okay, now first of all you have to calculate the, you don't have to calculate the likelihood function or anything else, you have to calculate the moments. So you start with calculating the moments, that is beta alpha upon alpha into infinity 0, the range is that xr into x alpha minus 1 e to the power minus beta x dx. When you solve it, okay, what will you get? You will get beta alpha plus r beta alpha plus r, and when you solve these gamma functions you will get alpha plus r into alpha a beta r. Okay, now just put the value of alpha r. So first of all calculate the first moment, that is what, alpha plus 1 and alpha beta. Or if you don't want to calculate like this, just you have to calculate the calculate directly the first moment, then calculate the second moment, you can do that. But the easy way to doing this is this part, because here you only have to integrate only one, and by calculating the other moments you have to just put the value of r here. So you will get alpha by beta. Okay, then you calculate the mu2, that we will get what, alpha plus 2. See, if you don't calculate it in this way, like you don't calculate in this way and you calculated for the mu1, then you have to calculate for mu2 as well. Okay, but when you calculate the first, that is mu r, you only have to put the value of r. Okay, see how easily it will be make, that is alpha plus 1 alpha upon beta square. Okay, so when you divide it, and you have to use some of the logics, that when you divide, how would you perform after that, because it will only depend on you. So I will just divide these both. If what we get, I will get this 1 upon alpha, that is 1 upon alpha plus 1. So from here I get the alpha value, that is mu1 dash square upon mu2 minus 1 square. And how will you get the beta? Just alpha upon mu1 dash, that is mu1 dash upon mu2 dash minus mu1 square. Okay. So alpha estimate will be m1 square into m2 dash minus m1 square, and beta estimate will be m1 into m2 minus m1 square. This is your estimates. Okay. Okay, let me do one another questions with take the different example. Okay, suppose x is a random variable that take value 0 1 2. Okay, with probabilities 4 theta upon 4n plus 1 upon 2 1 minus theta upon n, then theta upon 2n plus alpha upon 2 1 minus theta upon n, and theta upon 4n plus 1 minus alpha upon 2 into 1 minus theta upon n. Okay, where n is known number, alpha theta is unknown parameters, so basically you have to estimate these. Okay, 75 independent observation of x yields in 0 1 2 families with frequency 27 38 10. Means in 0 there are 27 values, in 1 there are 38 values, and in 2 there are 10 values. Okay, you have to estimate theta and alpha by the method of moments. Okay, let me write it. Estimate theta and alpha by method of moments. So how will you approach? Let me change the color. Yeah, first of all calculate the expectation, that is 0 into, because the probabilities are given, it is not x, it is multiplication, 4 theta upon 4n plus 1 upon 2 plus theta upon n plus 1 into 2n alpha by 2 1 upon theta upon n plus 2 into theta upon 4n plus minus alpha by 2 1 minus theta upon n. Okay, okay, so after solving this what you will get? You will get theta upon n plus 1 minus theta upon n into alpha by 2 plus 1 minus alpha. Okay, so just try to solve it, and the final value will get 1 upon 2 upon theta upon n. Okay, now calculate the expectation of x square, that is 1 square, see 0 is 0, so that we don't need to take this, n plus alpha upon 2 plus theta upon n, 2 square theta upon 4n minus 2 1 minus theta upon n. Okay, so after you will solve this, you will get 2 minus theta upon 2n minus 3 up by 2 alpha 1 minus theta upon n. Now what is the sample frequency? X and f. 2 27 38 10. Okay, so calculate it. Mu2 is what? 1 upon n sigma fx, that is 1 upon 75 into 38 plus 20, that is 58 plus 75. Now not sorry mu2, it's mu1, I'm sorry, and its mu2 dash is what? 1 upon n sigma f x square, that is 1 upon 75 into 38 plus 40, that is 78 upon 75. It is mu1, and you have just calculated this simply. Just put in the formula. I'm sorry, that is not, it is x here. Okay, now we can estimate the moment from here. See, 1 minus 1 minute 1 minus alpha upon 2, 1 minus theta upon n is what? 58 by 75. Okay, from here you will estimate it, and alpha upon 2, 1 minus theta upon n is what? 17 by 75. Okay, now substitute this. Two. Okay, sorry, so we have to substitute this in second equation, and the second equation is what? This is the second, it is the first. Okay, so when you substitute it in second, what we get? You get 2 minus theta upon 2 n minus 3 into 17 by 75, and you will get 78 upon 75. So from here theta is what? 42 upon 75 n. It is the estimate of the theta. Okay, and this is your equation number 3, and substitute in equation number 3. What you will get? Alpha upon 2, it is alpha into 1 minus 42 upon 75 is equal to 17 by 75. So from here alpha value you will get 34 upon 33.